So in our unit of electrostatics, we need to talk about a fundamental property of the universe. And if you recall, we have three fundamental properties of the universe when we're first studying physics: mass, time, and length. And mass we measure in kilograms, time is in seconds, and length is typically measured in meters. But when we're getting into electrostatics, we see that there's a totally new property of the universe that's fundamental, and that's charge. So we could put that down here. And that ends up being measured in these units of coulombs. So what we want to do here today is just outline what are some of the basic properties of charge that you need to know about. So the first thing obviously is just how do we represent it. The variable is lowercase q or capital Q, just depending on the context, and we'll see examples of that as we move forward through this unit. And then the units of charge is the coulomb, or capital C. So that's the basics. And then in terms of the fundamental properties, let's take a look at those. So the first one is that charge is quantized. And I'm not sure if you're, familiar with this word quantized and really what that means, but what it means is that charge comes in these multiples of the most fundamental charge you can have, which is the charge of a single proton or a single electron. So it comes in these discrete little packages. So you could think of it kind of like this, like if this was like a little box or something, you can have one of those, or maybe you could have two of these together. Let me draw another one like, oh gosh, trying to draw here. Okay, now we have two, and then you could go dot, 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 three. But we always have these multiples of individual boxes. You're not going to have half of a box. We look around in our world and there are things that are quantized. You have a single car, you have 3 cars, 5 cars. You don't have 1.25 cars. Same thing with people. You have 35 people in a room. Okay, you don't have 7.23 people. That doesn't make sense. So charge is quantized, and it comes in the fundamental, or it comes in multiples of the fundamental amount of charge, which is a single proton or a single electron. One way to talk about that is just to say plus or minus n, which is just an integer, multiplied by the charge of an electron, or you could also go like this, plus or minus n times the charge of a proton. I guess this plus or minus is kind of redundant if you're going to write out both the electron symbol and the proton symbol like that, but I think you get the idea. Now, just as an aside, if you go further in physics, you'll learn, if you get into subatomic particles, that this actually is kind of a lie. We historically learned about this first in terms of these being the most fundamental, the electron charge and the proton charge. You can go further, and you get into quarks, and those end up having charges of plus 2/3 and minus 1/3, which we won't be talking about now. And usually when we say charge is quantized, we mean it comes in these multiples of electron or protons, just for simplicity when first learning. Next, charge is conserved. And so we see if we have some system here, I've just kind of put an arbitrary box around a system, and we have 2 objects in the system. One of the objects has a charge of plus 5 coulombs. Notice that's not positive 5 electrons like you might see in a chemistry class when you're balancing equations. This is plus 5 coulombs. Which happens to be a lot of charges, or sorry, a lot of individual electrons or a lot of individual protons, depending on the sign of the charge here. But we got plus 5 for this object and then minus 7 coulombs for this object. So inside of this system, maybe just pause for a second and think about this. What's the total amount of net charge in the system? Okay, so hopefully you thought about that. And the way you do that, you just add it all up together. And plus 5 minus 7 would give us minus 2 coulombs. So no matter what happens, somebody could come along, or something inside of the system could cause these objects to interact in some way, and they could transfer charge back and forth. We could kind of model that by showing these things with arrows where they're, I don't know, in some complex interaction interacting. But at the end of the day, no matter what happens with the numbers, we better still have a net charge of minus 2. So you could maybe write, if you wanted to, some examples of what it could look like. Let's just do some erasing in here and try to do that. So come up with an idea of how we could change these numbers so we still have things adding up to minus 2 coulombs. Okay, well, maybe we could have, I don't know, a simple idea would be that this minus 7 coulomb charge decided to give maybe 2 coulombs of negative charge to the first object up there. So now it would have a charge of minus 5 coulombs. And because 2 of those negatives went over to the positive guy, that was plus 5 originally, now this would be plus 3 coulombs. And if you look, we still have a total addition of minus 2 coulombs. So a very simple idea showing that in any process in some closed system, I should make a note about that, so we're not allowing anything to come in or out, we're going to see this conservation of charge property hold. Now, charge quantization and the conservation of charge are kind of the two most fundamental ideas, but we'll lay out a couple other things as well that are important to think about with electric charge. Number 3, I would say, is that charge gives rise to what's called the electric force. And so we have a negative charge here, Q1, and a positive charge, Q2. I'd like you to pause the video and try to draw arrows that would represent the electric force that each one of these charges experiences. So which way will Q1 be pushed or pulled? And same thing with Q2. And at the same time, try to size the arrows correctly. For example, does Q1 feel a larger, smaller, or same size of force as Q2? Pause the video and try both of those questions. Now you likely know the direction of the force just from basic understanding in science. Like charges repel, so 2 positives would repel each other, or 2 negatives would also repel each other. And unlike charges attract, so these are unlike charges, so there's going to be an attraction, and the forces will be directed towards each other. And an important thing to know about the electric force is that it is pointed along the line, the straight line that joins the 2 charges. So if we were to come along here and draw a straight line that connects the 2 charges, then that electric force is always pointing parallel to that line. So we'd see a force like this and a force like this. And to be specific, this would be the force of charge 2 on charge 1. And this over here would be the force of charge 1 on charge 2. And if you've studied physics before, you have a little bit of idea of Newton's laws, then alarm bells should be ringing right now. I'll say this one more time. We've got the force of 2 on 1 and the force of 1 back on 2. What law is this? Yes, hopefully you're saying it. This is Newton's third law, and it also still applies always. It applies here with the electric force. Okay, so hopefully you're able to reason the direction of the force and that they're both experiencing the same size of newtons in each case because of Newton's third law, even though they have different charges. We've seen this before with mass and 2 objects with different masses, maybe the Earth, I'll just draw this up here, and then the Moon. The Moon is much smaller, but they both experience the same size of force. One accelerates more than the other, of course, and that would be the smaller object because we know of Newton's second law, which says that the acceleration of an object is directly proportional to the net force exerted on it divided by its mass. Right, so these are ideas that hopefully are familiar to you. All right, and one final thing we'll talk about here for just an introduction to electric charge is reminding you that when we're talking about the structure of atoms, the protons and neutrons are packed tightly in the nucleus, and that's where all the positive charge is. And then on the outside of the atoms, we have all the electrons and their electron clouds. And you've studied this in, hopefully, chemistry. And it's an important idea that you realize that it's this negative charge is on the outside of the atoms, because typically when we're dealing with charges being transferred from one object to another, the positive charges are kind of like locked inside of the nucleus of the atom, and it's the movement of the negative charges that is the easiest to do, of course. So just think about that when you're trying to visualize really what's going on in these atomic processes when charge is moving around for just regular atoms. Here's a simulation from FET, University of Colorado, great simulations. Here's a balloon, And for whatever reason, when this material of the balloon interacts with the material of the sweater based on the nature of the bonds and the types of atoms and things that are in balloons and in sweaters, when we rub by friction, when we rub against the sweater here, we see that we pick up excess electrons. We're ripping electrons off of the sweater, and now those are being deposited onto the balloon. Don't worry about like a mechanism for that. For now, we're just going to abstract it away and just say, well, this process of rubbing the two things together with friction causes this to happen. To really see why it would occur, you'd have to probably go into the details of the atomic structure and bonds and like quantum physics and all that. We're not going to do that right now. But you can see clearly now we have two objects that are charged. The sweater is charged up positively and the balloon is charged up negatively. We still have no net charge in the whole system, of course, if we think about this whole system being, what's in the sim, but we have charged objects. So if I let go, we can see, boom, now there's this attraction from the balloon straight to the sweater because one object is positive and the other is negative. Also notice that you don't see any of the negative charges trying to hop off the balloon now going back onto the sweater. And that's because these materials are what we call insulators. They don't transfer charge very easily, unlike metals. And when they do get charged up, they tend to keep the charge. And so now we can see an attraction. All right, so there we have it, a nice introduction to the properties of electric charge, a little bit about electric force, and we'll continue on in future videos outlining more things as we move through electrostatics.